When a mass tied to a string attempts a vertical loop, it faces a strict physical limit. If the mass lacks sufficient speed, the string loses tension, and the orderly circular path collapses into a chaotic fall. Analyzing this system through Newton's laws of motion requires calculating the specific forces acting on the mass at every instantaneous angle along the curve. Executing this through continuous vector calculus is inefficient. As the Maslow gravity consistently points straight down, but the mass's velocity vector rotates. The relative angle between them changes continuously, meaning the effective force must be recalculated at every point on the path. This leaves us with a difficult computational question. How do we calculate the exact launch velocity required at the bottom to ensure the system completes the loop without physically collapsing? To bypass the complexity of constantly shifting vectors, we must abandon the framework of instantaneous forces. We must map the entire system using states of energy. We accomplish this mapping using the work-energy theorem. This principle states that the total work done by all forces on a system exactly equals its change in kinetic energy. Mathematically, work is defined as the integral of the dot product of force and displacement. The dot product is critical here because it indicates that the total work done depends on the specific path the object takes relative to the force. However, conservative forces obey a different mathematical rule. For a conservative force, the total work done is entirely independent of the path taken. The force is the negative spatial gradient of potential energy. Gravity is a conservative force. This means we can map its exact physical effects throughout the vertical loop using a scalar potential field, bypassing the need to track individual force vectors throughout the motion. By translating the physical boundaries of the loop into the conservation of mechanical energy, we reduce a complex continuous vector problem into simple algebraic states. To apply this scalar approach accurately, we first verify the geometric constraints of the vertical loop model to ensure no other forces change the energy of the system. This diagram illustrates the forces acting on our mass at an arbitrary angle, theta. We have two distinct vectors to evaluate: the tension pulling inward from the string, and the weight, mg, pulling straight down. Using the geometry of the circle, we isolate the radial component of gravity. The term mg cosine theta points directly along the line of the string, parallel to the tension vector. Now we apply a crucial insight. The mass is physically constrained to move in a circle, meaning its instantaneous velocity is tangent to the curve. Therefore, the tension vector, which points precisely toward the center, is always strictly perpendicular to the mass's motion. Because tension is perpendicular to displacement, the dot product of the two vectors is zero. Consequently, the string itself does zero mechanical work on the system. We formalize this constraint with the instantaneous radial force equation. The net force pointing toward the center, tension minus the outward radial component of gravity, must equal the centripetal force required to drive the circular path, mv squared over r. Since the string does zero work, and gravity's work is accounted for by the scalar potential field, the total mechanical energy of the mass remains perfectly conserved throughout the entire circle. With energy conservation verified, we pinpoint the physical boundary condition required to complete a full loop. The string must maintain its structural integrity. It cannot go slack at the highest point. In this schematic of the vertical plane, point C represents the apex of the circle. To prevent the string from slacking, the mathematical condition is clear. The tension at point C must be greater than or equal to zero. We apply our radial equation at this apex. At point C, the angle is 180 degrees, so both tension and gravity point straight down toward the center. By setting tension to zero at the absolute limit and solving for the velocity, we find the critical velocity. To maintain the circular path, the mass must travel across the apex at a speed of at least the square root of g times r. We now map this critical top speed back to the launch conditions. We evaluate the path from the origin, point A, straight up to the apex, point C, marking a total vertical height change of 2r. Because mechanical energy is conserved, the total kinetic and potential energy at the bottom must exactly equal the total kinetic and potential energy at the top. We substitute our known variables. Setting initial potential energy to zero The kinetic energy at launch must equal the new potential energy at the top, mg times 2r, plus the kinetic energy dictated by our critical apex speed. Solving this equation reveals the minimum requirement for a full loop. To sustain tension through the entire curve, the initial launch velocity, u, must be at least the square root of 5gr. Having defined the upper boundary, we evaluate the secondary threshold. This boundary dictates perfect pendulum-like oscillation, where the mass stops and reverses direction without the string ever going slack. Back on our geometric model, the limit for this pure oscillating state occurs at the horizontal axis, marked as point B. For pure pendulum motion, the velocity must drop to 0 exactly at or before this horizontal line. The string cannot slack in this lower quadrant. Because the angle from the vertical is less than 90 degrees, the cosine component remains positive. Even when velocity drops to 0, the radial component of gravity ensures tension remains greater than 0. We apply mechanical energy conservation again. We evaluate the exact state where velocity drops to 0 at point B, which sits at a vertical height of exactly r. Equating initial kinetic energy to pure potential energy at point B yields the pendulum condition. To oscillate without slacking, the initial velocity must be less than or equal to the square root of 2gr. By identifying these critical boundaries, we map the continuous motion of the system into 3 distinct physical outcomes, dictated entirely by initial kinetic energy. In the first outcome, if launch velocity is at least the square root of 5gr, the system possesses sufficient energy to maintain tension against gravity through the entire gradient. The loop completes. In the second outcome, if velocity is less than or equal to the square root of 2gr, the mass lacks the energy to reach the horizontal threshold. It remains trapped in predictable pendulum oscillation. The middle ground occurs when velocity sits between these boundaries. The system pushes past the horizontal axis, but lacks energy to reach the apex. Tension drops to 0 while in motion, causing the mass to enter a projectile trajectory. By utilizing energy states, we bypass the need to calculate instantaneous vector angles along the path. The path-independent nature of mechanical energy conservation allows us to define continuous movement by comparing only 2 static points, the bottom and the top. Evaluating the spatial derivatives of a potential field provides a powerful method for mapping the stability limits of a system. It defines the exact specific thresholds where motion remains continuous and where the internal constraints of the system will fail.